Welcome, grade 12. Welcome to this lesson. We're doing paper 1, the trial of 2024 from the Gauteng province. I'm going to do the entire question paper. But here's the thing, you have to pause each and every question and do it by yourself before you watch the answers. That will help you to understand and familiarize yourself with the question papers. Let's cut the chase. 1.1, it says an air bubble in a tank of water is rising vertically at constant velocity. The forces acting on the bubble are X, Y, and Z as shown below. Diagram not drawn to scale. Here are the forces, the vertical forces. We have an upward force and two downward forces. Now it says here, which option is incorrect with respect to the three forces acting on an air bubble? Take upward as positive. We have an important information here in the statement. It says constant velocity. That means the acceleration is zero and the F net is equal to 0. So let's start by doing this. F net is equal to 0, and then the only force that is positive here, it's X, and then Y is negative because it's going downwards, and the Z is negative equal to 0, right? Now, we're going to use that as a guide to our question. We check which one is incorrect. Now, if we have X is equal to Y plus Z, is it possible there, if we take Y to that side and Z to that side, they're both going to be positive. So this is the correct option. Now let's look at B. It says Z is equal to the sum of X and Y. If we take the Z to that side, we're going to have X minus Y. So this is not possible. This is not possible. And then let's look at the third option, which is C. Y is equal to X minus Z. So if we take Y to that side, we're going to be left with X minus Z, which is, this is the correct option as well. Now, let's look at the last option. It says X is bigger than Z and Z is bigger than Y. Yes, that's possible. If you look at this, X is equal to the sum of these two, which means X is bigger than both of these two. So X is equal to the sum. So X is bigger than Z and Z is bigger than Y. So this is the correct option. So the answer here is B. Question 1.2. A person stand on a scale in a lift. The motion of the lift is given in terms of its acceleration. Which situation represent weightlessness? Now let's talk about the weightlessness first. The weightlessness is a state of the person or an object when the person experiences the sensation of weightlessness, when the person feels light and it feels like there's no force of gravity, but there is the gravity, the force of gravity. So there is the force of gravity. Let's look at the first option. The person moves at constant speed and the acceleration is 0. This is not an option. This is not an option. There is the gravitational acceleration in the weightlessness. And then there is a gravitational acceleration in B, but it moves up. Okay, have you ever felt when you're in a lift and the lift it goes down and you feel your body light and you feel like you're floating in the lift when it goes down? So this is not an option because it goes upwards. Let's look at C. The lift is accelerating downwards and there is an acceleration that is 9.8, and I think this is the best option. Now let's look at D. D, it's going downwards, but it's going in an acceleration that is 5 meters per second. No, this is not an option. Remember, the weightlessness, it's when the only force is the gravitational force, right? And it goes down. So C is the best option here. Now, 1.3, it says a golf ball falls vertically downwards from rest in air and bounces up to the same height which it was dropped. The graph below shows in the acceleration of the golf ball with time. All effect of friction be ignored. Let's draw this. This is the height This is the height, and this is the ground. So this ball is dropped from here. So if it's dropped from here, it's gonna do that motion and bounce. So it starts here with an initial velocity that is zero because it's dropped, and then it hits the ground, which is going to be the final velocity, and then it bounces and reaches the same height again. So if it reaches the same height, which is the final velocity, there will be zero, and the velocity that leaves the ground, it's the initial. But what is this initial and this final velocity and this initial velocity are going to be equal, but in opposite direction, are going to be equal in opposite direction. This kind of elastic, kind of collision here, it's elastic collision. Once the velocity before collision is equal to the velocity after collision, it's elastic. So it means that how do we know it's elastic? Because they told us it's going to reach the same height. So if it reaches the same height, that means this type of collision, it's elastic. The velocity before collision and the velocity after collision, they are equal, right? Let's this is the acceleration time graph. The acceleration time graph for this, the acceleration is constant, it's 9.8. But what is happening in this curve, it shows that there is a bounce, right? This is the bounce, right? Now it says here the following statement are made about the golf ball's motion, right? Now it says it experiences the maximum speed at the minimum height. So here at the minimum height is here. When the height is zero, it experiences the maximum speed because the ball, its velocity increases further. When it gets there at the minimum speed, it experiences the maximum speed. That's correct. This is correct. And it says its displacement falling is equal to the displacement rising. Yes, this is correct. We were told that it bounces and reaches the same height. So the displacement from there to there is the same from the ground to the maximum height. So this is correct as well. Now let's look at 3. It experiences the minimum speed at the maximum height. At the maximum height, if you look here, it experiences the minimum speed, which is zero. And also here at the maximum height here, it experiences the minimum speed, which is zero. This is also correct, right? So the correct option here is what is D. I hope that makes sense. 1.4. 1.4, a ball of mass m moving with a velocity v collides head on elastically. Here's the word again, elastically. The elastically simply means that the total kinetic energy before is equal to the total kinetic energy after. That means the velocity before collision and the velocity after collision, they are equivalent, just like the previous statement. It says a ball M is moving with a constant with a velocity v and collides head on elastically with with another body of the same mass m, right? With the velocity v in opposite direction. So these two objects, they are colliding. They colliding elastically. So when they collide elastically, their initial velocities before collision is going to be the same with their velocities after collision, but it's going to be in opposite direction. Let's look. It says after collision, both ball moves with velocity v. Their velocities, initial velocities were v. Yes, this is correct, but that's not enough information. Let's look at B. Both ball travel in opposite direction with the speed v. This is correct, and it has details. This one. Now let's look at the other option. It says both ball move to the right angle. Incorrect. They can't move at right angle. One ball comes to rest and others travel. This is incorrect because we are told that this is elastically. Elastically means the velocity before collision is going to be the same as the velocity after collision. So the velocity before collision, it was v, and their velocity after collision, it's v, but in opposite direction. So the correct answer there is going to be B, right? I hope I do make sense, grade 12s. I hope you are pausing the questions as we move along and you do it by yourself. before you answer. You watch. 1.5, it says a mass is lifted from rest on the ground to the point H as shown diagram. So this is the object is lifted to the height H at point H. It says P is increase in gravitational potential energy. As the object is lifted, there is a gravitational potential energy. It says K is the kinetic energy of the mass at point H. So as the object is lifted from rest, there is an increase in speed. That means there is a kinetic energy. Kinetic energy and the speed, they are directly proportional. Now it says which expression is equal to the mechanical energy work done on the mass to move from the ground to point H. Right, guys, the mechanical energy here the mechanical energy here is equal to the sum of the gravitational potential energy and the kinetic energy. So the option here is A. It's the gravitational potential energy plus the kinetic energy. The mechanical energy is equal to the kinetic energy plus the gravitational potential energy. But in this case, the kinetic energy is K and the gravitational potential energy is P. So the correct option is A. Now, 1.6, it says, what does the term redshift mean? The redshift, guys, in terms of the Doppler effect, and it's when something is redshifted, that means it's moving away. When it moves away, that means its wavelength it's increasing, and its frequency it's decreasing. So one of the things that the redshift explained, that our universe is expanding. Yeah, right, our universe is expanding. So the expansion of universe, it shows, or it proves the redshift, right? So the object speed in a space, it doesn't talk about the speed in a space. The color of a distant galaxy, no. The expansion of the universe, correct. Increase in temperatures, increase in objects temperature, no. So the correct answer is 1.6 there. Now 1.7, it says, which of the following graphs has a slope that equal to Coulomb's constant? We know Coulomb constant from the formula, where E is equal to K Q over R squared, or that formula that says F is equal to K Q1 Q2 over R squared. We're talking about that one. Now let's look at this graph. So looking at this graph, we are going to check if we're going to get the gradient as E as K. Let's look at, if we say change in E, which is change in Y over change in X, over Q is equal to, and then we're going to substitute E as that one, Q1 over R squared divided by Q. So the Q and Q will cancel. So the gradient here is going to be K over R, which is incorrect. Let's look at B. If we say change in Y over change in X is going to be change in E over change in X. R squared is going to be KQ1 over R squared divided by R. So the R and R will cancel. So we're going to have KQ as a gradient there, which is incorrect. Let's look at C. Let's look at C. This one, change in Y over change in X. If we say change in Y over change in X, and then we substitute the E by KQ1 over R squared, all divided by Q 1 over R squared, right? So these two are going to cancel, these two, and then we're going to be left with K there. If you invert to change the division into multiplication, so those two are going to cancel there. So we have the K. So that simply means that D, it's an incorrect option. So the correct option here is C, guys. We get K. Let's look at 1.8. 1.8 says three resistors are connected in a circuit shown in the diagram below. Here's the circuit. The total current, it goes this way, and then it splits, and then it combines and then it passes there. So that means our circuit, it has a parallel section and the series. Now, and it has a total current and a total resistance, right? With this, there's a total current and a total resistance. Now, it says now that a fourth resistor is connected parallel to the 4 ohm resistor, right? Here's the third one. A fourth resistor is connected parallel to the 4 ohm resistor, right? Theoretically, you need to understand, guys, whenever you add the resistance in parallel, the total resistance decreases. So if the total resistance decreases, the total current will increase, right? So here there's a decrease in what? In a current, right? Let's look at the 8 ohm resistor. What happened to the current now? That current that we had here before we added that resistance there, it was little, but now it has increased. That means here the current has increased. So that means the power of this resistor is gonna what? Is gonna increase due to this formula that says power is equal to current times resistance. The power and the current are directly proportional. The increase in current, there will be an increase in power, right? Let's look at this one. This one, the current before this, it was a bigger current that only passes here without this resistance. Now, since the current has increased, now the current is more, but the current now is divided in half. The other half we're going to go this way, the other half is going to go that way. So here, seemingly the current has what? Decreased, and therefore the power will what? Will decrease as well due to this formula. So we're going to look for the formula that has an increase and the option that has an increase and a decrease, which is the option that has an increase and a decrease. It's D, right? 1.9. It says an immersion heater can be operated either an AC power supply or a DC source. The graph below represent the potential difference when an AC power supply is used. Do we know the graph of the AC? It's like that. It's a sine graph, right? We're given there the Vmax is the 12. It's the Vmax, and that's the Vmax. That's our Vmax. Now the question, it says, what DC supply voltage would produce the same rate of heating? So for the same rate of heating, the DC current won't produce the same. It will produce the what? The VRMS. So that means the VRMS will take the Vmax and we divide by the square root 2. So it's going to be 12 divided by square root 2. So the option here, which option that has, this is not an option, not an option, this is an option. So the answer here is what? Is C, right? Now let's look at 1.10. 1.10, it says the work function of a metal is that. That's the equation for the work function. If this metal is illuminated with the light of frequency, that is 3 times the threshold frequency, the maximum kinetic energy of the photoelectron will be. So now they say the energy of the light, the frequency of the light, of this light that is used there is 3 times the threshold frequency. In other words, that means the energy is equal to H times, instead of the frequency, you're going to substitute the 3 times the threshold frequency. That means it's going to be 3HFO, right? Now they wanted the kinetic energy. We use the formula that says energy is equal to work function plus the kinetic energy, right? The kinetic energy is going to be energy minus the work function, and then we substitute the energy. The energy, it's a 3HFO minus the work function is HFO. So it's going to be 3F HFO times 1FO, it's going to be 2AFO. So this is not an option. This is an option, not an option, not an option. So the answer there is B. Question 2. This is the Newton application, or the Newton question. It says a toy train of mass of 2 kg and a toy car of 1 kg are attached by a light inextensible string. The car train system is pulled on a rough slope at constant velocity by a rope with a force of T2 and on the slope of 10 at 10 angle inclined. So the very important information there, it's constant velocity, the acceleration equal to 0, and the net force is equal to 0. And it's pulled on a rough, that means there's a friction there, there's a presence of the friction there, right? Another thing before we go to the questions, let us label the forces that are acting on each object. There we have a normal force, we have a gravitational force, we have a tension force, which is T1, we have an FG parallel, and we have a friction force, which is FK. And there in the train, we have a T1, we have FG parallel, and we have FK. So those are the forces that are acting there. And then we have a T2 there, and yeah, that's what we have. And then we have the components of the T2. So we have Tx, which is the horizontal component, and the Ty there. And we have the normal force, we have Fg, we have Fg perpendicular. Very important to understand all the forces that are acting there. Now in 2.1, it says explain the term net force. The net force, guys, you answer it according to the exam guideline. It's the sum of the forces acting on a body of two or more forces. It's a sum acting on a body of two or more forces acting on a body, or you can say it's a single vector that has the same effect of two or more vectors together, right? I'm not going to write it. 2.2, it says draw a label free body diagram of the train toy. So let me write it here. Before that, in order to guide me to draw an inclined free body diagram, I resemble the incline by the broken line, and then the train by a dot, right? Let's draw the normal force. Normal force, do you see? My normal force is perpendicular to the surface. It should be perpendicular. Guys, it can't go vertically like that, the normal force. It should be perpendicular to the surface. And then we have an FG. Remember, the free body diagram that we are drawing, it's the one that has no components. So the next thing that I'm going to draw, it's this force, the T2. The T2, it's at a 10 and 10 degree angle, right? And we have the frictional force. And what else do we have? We have a T2 force, a T1 force, that T1 force there, right? That's our free body diagram. Should be straight, guys. It must be a straight line using a ruler there, right? That's the free body diagram that is needed, guys. That's your 5 marks. It's 5 forces. Let's go to 2.3. 2.3, it says a tension T2 is increased to 20. Whatever force it was, this force now, it has increased to 20. It is 20 now, causing the system to accelerate up the slope. Calculate the magnitude of the acceleration of the system if the friction acting on the car is 1.5 newtons and that on the train it's 2. Now it's accelerating. It was not accelerating. The acceleration, it was 0 because it was moving at constant velocity. Now it's no longer moving at constant velocity. Now what are we going to do in 2.3, guys? We're going to use the the simultaneous equation. Why? It's because we want the acceleration of this system, and yet we do not have this tension here. So we have two unknowns. Two unknowns, that means it's a simultaneous equation. So I'm going to create an equation for the train first. Train, and using the formula F net is equal to MA. You must write this equation, guys. It's going to give you marks. Then I'm going to go and check the forces that are acting on the train that is parallel to the surface. So the forces here, it's the tension and the frictional force and the tension and the FG parallel. So it's four forces, and I choose my direction, choose up the slope as positive. That means the TX is going up the slope is going to be positive, and all of them are going down the slope, which is the FK, FG parallel, and T1 is equal to MA. And then I substitute. The TX is the same as FX. So it's going to be the force, we're told the force is 20. So it's going to be 20 cos, and the angle of the incline is not that one, not this one, this one. It's going to be 10 minus the frictional force, it's 2. The FG parallel, it's mg sine theta, which is going to be the mass of the train is 2. So it's going to be 2 times 9.8 sine. The angle, it's 20. The angle of an incline, it's 20. We're using that one. Minus T1 is equal to the mass is 2 times A. And then when you punch this in the calculator, you will get 10,9925. I'm not done. I don't want to round off into two decimal place. Minus T1 is equal to 2A. And then I'm going to make a T as a subtract of the formula. Taking the T to that side, it's going to be T1 is equal to 10,9925 minus 2A. The 2A is going to go in this side. This will be my equation 1. I created the equation for the train. Now let me create the equation for the car. F net is equal to MA. So F net is equal to MA. I'm going to the car and check the forces that are acting there horizontally or parallel to the surface. It's 3 of them. It's the FG parallel, the FK, and the tension force, right? So it's the T1 that is positive, the one that is going up, and FG parallel that is going down the slope, and the FK that is going down the slope is equal to MA, right? I hope I make sense there. And then I substitute. I don't have T1, and the FG parallel is going to be 1 times 9.8 sine 20, the angle of an incline, minus the frictional force. We were told it's 1.5 of the car, so it's going to be minus 1.5 equal to 1 times A, which is 1 times the acceleration. So T1, when I punch this in the calculator, must be very careful, must include this negative. When you punch this in the calculator, it's going to be negative 4,85 equal to A. And this is equation what? 2. Now what I'm going to do now, I'm going to sub both equation. I'm going to substitute equation 1 into equation 2. So equation T1 is equal to that. So in this T, I'm going to substitute that. So it's going to be 10,9925 minus 2A minus 4,85 equal to A. So when you punch this in the calculator, 10,99 minus this is going to be it's going to be 6,1425 equal to, when I take this to this side, it's going to be 3A, and I divide by 3, the answer is going to be 2,05 meter per second squared. That's the acceleration of the toy train car system. Now let's go to 2.4, the last question here. It says, halfway up the slope, the string T1 breaks and the car rolls down the slope. Does the friction of the train increases or decreases or remain the same while it's moving up the slope? Guys, if while this was accelerating at 2 meters per second, and then there's a 20 Newton force that is pulling this train, which pulls the whole system. So this T1 breaks, which is snaps this string, right? So this train will continue moving in that direction. Now the question is asking now, is the friction of this that is experienced by the train change? The answer is no. Why it's not going to change? Let's write the answer here. It's 2.4. So for me, it's going to remain the same. Why? Let's look at the formula of the friction. The friction, it says friction is equal to mu k times what? Normal force. Friction is mu k times normal force. The normal force has not changed, and the mu k, sorry, the mu k has not changed. The description of the surface has not changed today, and the normal force as well has not changed. So if the normal force and the mu k has not changed, that means the friction will remain the same. So the answer here is remain the same. Remain the same. Sorry about combining those two words. So the reason for that, it's 3 marks, which is that's 1 mark, so I must have 2 points. The reason for that, you will say the normal force, is the same, did not change. And secondly, you will say the frictional force is directly proportional to the what? To the normal force. So you can write the normal force like that. Question 3, let's look at the vertical projectile of motion. It says a tennis ball falls freely from rest, very important, from point A, which is 44 meters above the ground. The time taken to fall to the different position B, C, D is given in terms of time T as shown below. Ignore all the effect of friction. Let's look at this, guys. Now, here, this is an object is released there. Once it's released there, that means the initial velocity at point A is 0. And it's released, it's going to travel this direction, and then we're going to choose that direction as positive. Downward is positive. That means our gravitational acceleration is going to be positive. Very important to choose the direction. So it's going down, it's going to travel 44 meters down, right? The 44 meters is going to be positive because we chose down as positive, right? But if you're looking here, it has a different position. From here to here, we are given the time at travel, it's 2t seconds, but we don't know what is t. And then from B to C, it traveled the t seconds. And then from C to D, it traveled the 3t seconds, right? But we know as it goes down, the velocity increases, right? Now let's draw this and see what we can get out of this. Very important to make a diagram. This is the height where it was dropped. It was dropped here. It was dropped here. So it's going to go down and hit the ground. And then when it hits the ground, so we know this is A and probably B there and C there, and then and D there, right? So now let's answer the question. Define the term free fall. Guys, it's very important to define all the definitions according to the exam guideline. A free fall is a motion of a body when the only force acting on it, it's a gravitational force. Very important to look at the exam guideline. 3.2, it says calculate T. So when we calculate t, it's going to give us what is the time here. What is the time here? We just substitute t. So what are we going to do in 3.2? We have an initial velocity, and which is 0, and we do not have the final velocity. We're going to use the whole segment, guys, from there to there in order to get the t. And we know the t, it's supposed to be positive, but we don't know the displacement there. It's going to be, we're going to use 44. If we're using the whole motion, we're going to use 44. And then the time that we have from here to here, it's going to be 2 plus t plus 3. It's going to be 6t. So that's the time we have. We have 6t, right? But what we are looking for, we are looking for t, right? So which equation is suitable for that? So we're going to use this equation that says change in y, vi change in t plus half a t squared. The reason we use this formula is because we only have initial velocity, because the final velocity at this segment that we choose, we don't have the final. So that's why we use that one. So we substitute our displacement, which is positive 44, and the initial velocity is 0. So this side is going to be 0 because it's 0 times 60. And then the half, the acceleration is positive, and the t is 6t, and then we square. So when we square there, it's going to be a 6t squared. When we square, our answer there is going to be we're gonna have 44 is equal to, when you punch this in the calculator, it's gonna be 176,4 t squared, this part. And then we divide by t, we divide by 176, 44 by 176 is gonna be t equal to a square root, because there's a square there. It's gonna be 44 divided by 176,4. So the answer is going to be 0.499 seconds, which is in two decimal places going to be 0.5 seconds. Now we have the t. We know the times of different sections or different positions now. So in 3.3 now, let's answer 3.3. 3.3, it says calculate the height of ball at point C. Very important. It doesn't want this displacement from there to there. It wanted the height. It says, what is the height? That means above the ground. So what are we going to do? We're going to calculate this displacement and minus from this one, right? So we're going to use this segment. In this segment, we have times, it's 2t plus the t, and the 1t is going to be 3t, and then we use the time. So let's go for it. So what are we going to do? We're going to say it's 3.3. So we have the time. The time is 3t there, but we have the t now at 0.5. So we're going to substitute the t. It's going to be 1.5 seconds. And then the initial velocity we have is 0. The final for that segment from A to C, we do not have. The displacement is the one that we want, and we know it's going to be positive. We wanted the displacement from A to C. So this displacement is from A to C, right? What else do we have? Okay, we're going to use the same equation, vi change in t plus half at squared. The displacement is the one that we want. The initial is still 0, so this is going to be 0. Half the acceleration is 9.8, and then the time now it's 1.5. 1.5, don't forget to square there. It's going to be 11,025 meters. The 11,025 meters, it's a displacement. It's a displacement from A to C. So we're going to say this minus A to C, so to get the height above the ground. So the height is equal to 44 minus 11,025. So when we minus that, we get the 38, not 38. We're getting 32,98 meters. So that's the height above the ground. This from here to here, it's 32.98 meters. That's what the question wanted. 3.4, it says if after the first bounce the ball reaches height C, and sketch the position time graph for the ball from the moment it's dropped until it reaches point C after the bounce. Show the following: the time value at T, D, and C before the bounce in terms of T. So we're showing the time in terms of T, not the times. The height AC, take the ground as a reference point. So how we're going to draw this graph, it's going to be like this. This is our graph, the position versus time, and then we are told we take the ground as a reference. When we take the ground as a reference, guys, let me show you here. When we take the ground as a reference, that means that this part is going to be your zero in your Cartesian plane. It's going to be like this. So your graph basically is going to be like that. This is the ground, so this is going to be your zero. So your Cartesian plane is going to be there. It's like that. So the ball, it goes down that way and hits the ground. So this is your point A, and let's say this is your B, and this is your C, and this is your D. Okay, let me write D inside, and this is your D. And then they say it bounces to a height C, right? So your height C. So your height A, it traveled the 44 meters, and it goes to the height C, which is the one we just calculated, which is going to be 32.98, right? And then they said we should show times, right? The time, guys, if you look at this, the time, they want us to show the time at the times for D and C in terms of T. The time for C, guys, here, let's start with the C. The time for C, it's what? From there to there, it's what? It's 2 plus 3 plus 2 plus 1, it's 3T. So this time, this is the time they want, it's 3T, right? And then the D, the time for the entire motion, the D for the time for the entire motion, it's 2T plus 1T plus 3T, it's 6T. So that means it's what? It's 6T, right? That's what they want, guys. Basically, that's what they want. They didn't require these things and this labeling. I was just labeling it for you to understand. Let's go to question 4. Question 4, it's an impulse momentum question. A wooden block with a mass of 150 grams is freely supported using the brackets at a height of 2 meters. When a bullet of 50 kg is fired vertically into the block as shown below. Guys, here's the wooden block as supported there by the brackets, and it's just placed there, right? And the height from the wooden block, it's 2 meters, right? And here's the bullet. The bullet, it travels with a velocity of what? Of 200 meters per second. It's a constant velocity, right? It's a constant velocity. So the bullet is going to hit that, and surely this is going to move. This block is going to move with the bullet, right? Now it says the bullet is embedded. It embeds itself into the block, and the bullet block system rises vertically into the air for a few seconds, and then it falls to its original. So the block is going to move maybe to that position with the bullet inside. The bullet is embedded inside, right? Now the 4.1, it says 4.1 state the law of conservation of mechanical energy, right? The law of conservation of mechanical energy, guys, it says the total conservation of mechanical energy. No, sorry, we must use the exam guideline, guys. The law of conservation of momentum, sorry, not mechanical, law of conservation of momentum. In words, it says the total linear momentum in an isolated system remains constant or conserved exam guideline, guys. Very important. I hope you paused this question before and then you answer it by yourself. 4.2. The 4.2 now, it says calculate the magnitude of the velocity of the bullet block system after bullet become embedded. So they wanted the final velocity of both the block and the bullet, right? So what do we have first? What do we have? Do we have the initial velocity of the bullet? Okay, let me write them here. 4.2. The initial velocity of the bullet, I'll say bull for the bullet, it's 200 meters per second, right? And the initial velocity of the block is 0 because the block, it was stationary. So since now they move together, the bullet is embedded, so they're going to be a system, I'll say BB, which is a bullet block system. So they want the final velocity of that. And then we're going to choose vertically upward as positive, right? And then you must remember their masses are combined. Their masses are combined, the bullet block, when they are a system, right? It's very important, that information. And the mass here is 150 of the block, and the mass of the bullet is 50 gram. So the 50 divided by 1000 is going to be 0.05 plus, and the 150 divided by 1000 is going to be 0.15. So the mass is going to be, when you combine that, it's going to be 0.20 grams, a kilograms, the combine of the mass after collision. So what are we going to use, guys? We're going to use the conservation of momentum. The momentum before is equal to the total momentum after, total momentum before. So it's going to be the momentum of the block, and the momentum, the initial momentum of the bullet, right? Of the bullet, and then block plus the bullet, and then the times by the velocity. Because remember, guys, they are a system after. So the mass of the block, it's 0 comma, the mass of the block, is 150, which is at 0.15 times the initial velocity, it was 0, and the mass of the bullet, it was 0.05. We times by the initial velocity. The initial velocity, it was 2000. It was going in the positive direction, and then the combined mass, as I've done there, it's 0.20, and we want the final velocity. And then when you do the math, and you divide by 0.2, the final velocity of the bullet block system is going to be what? 50 meters per second. That's the final velocity in which the bullet and the block are going to move upwards with. Now, 4.3 is the collision between the bullet and the block, elastic or inelastic collision, explained by using calculation. So we're going to explain it by using calculation in 4.3. We're going to calculate the momentum before and the momentum, the total kinetic energy before. Total kinetic energy before is equal to half, which is the kinetic energy of the block before, the kinetic energy before of the block, plus the kinetic energy before of the bullet, square. So the kinetic energy of the block before is going to be 0 because it has no velocity, and the kinetic energy of the bullet before, the mass of the bullet, it's 0.15. No, it's 0.05. 0.05 times by the velocity of the bullet, the initial velocity of the bullet. So the answer is going to be 1000 joules. And then we're going to calculate the total kinetic energy after. And then we substitute the mass of the block now. The mass of the block, okay, it's combined, the mass of the block plus the mass of the bullet. You can do that. You can combine the two now in this case. So let's get the mass of the block. We calculated it's 0.20 or 2, and the final velocity we got it was 50. So it's gonna be 250 joules. Now if you look at these, the kinetic energy before and the kinetic energy after, they're not equal. So you will say the total kinetic energy before is not equal to the total kinetic energy after. Therefore, the collision is what? Is inelastic. Inelastic collision. This collision is inelastic, right? Since because they are not equivalent. Now let's go to 4.4, which is the last question in question 4. On a different occasion, the bullet is fired closer to the wooden block at the same velocity. It exits the block. It exits the block with an upward velocity of 195 meters per second. So the bullet now is fired closer there, and then it emerges. The bullet, it emerges, it come out there with the final velocity, right? So what we have now, we have a final velocity of the bullet, right? The final velocity of the bullet. Now it says if the net force exerted on the block, by the block on the bullet is this one. So when the bullet hit a block, there's a force that they exact on each other. It's the same force but in opposite direction. So when they say that force that the block hits the bullet downwards, it's 5 newtons. And calculate the time it takes for the bullet to exit. So they wanted the contact time when the bullet was emerging. The bullet was moving through, so it was a contact time, and this time it would take to emerge there. So very important there. Okay, let's use this space to calculate 4.4. 4.4, we want time, right? We have the force, and right, remember guys, we chose up as positive. So the force that the block exact on the on a bullet is going to be negative, because it's going downwards, the force that the block exact on the bullet. So what do we want? We want the time, and we have the initial velocity. The initial velocity of the bullet is 200 meters per second, and the final velocity is 195 meters per second. They both positive because it's still going up, right? So we're going to use the impulse momentum theorem. So it's going to be F net change in t equal to the change in momentum. Okay, instead of that, I can say mass into V final minus V initial, right? And then we substitute. The force is -5. We want the time, and then the mass of we use the bullet, right? The mass of the bullet is 0.05, and then the final velocity is 195, and the initial is 200. And then if we divide by -5 both sides, so the time, it will be 0.05 seconds. That's the contact time. That's the time for the bullet to emerge. It takes to emerge out of the block. Let's look at the question 5 now. Question 5, it's a work, energy, and power question. An ice skating of mass of 53 kg moves on a frictionless surface AB. So this surface is frictionless, with a velocity of 6 meters per second. So the velocity that it moves here, it's what? It's 6 meters per second, and it slides up a rough. That means there's a friction there now. There's a friction there, a rough inclined surface BC until coming to stop at point C. So the velocity here is 0. 1 meter above. So this is the height that we're given there. It says the angle between an inclined and the horizontal is theta. We're not given the angle. and we do not have the displacement as well there. Now 5.1, it says state work energy theorem in words. Guys, it's very important to use the exam guideline. The work energy theorem, the work energy theorem in words, it says the net work done is equal to the change in kinetic energy. Basically, you can use this formula to define that. The net work done is equal to the change in kinetic energy of an object, right? Um, Now it says draw a label free body diagram showing all the forces acting on the skater at point C, right? At point C, guys, let's okay. This is important. There's a friction, and what else is important? No friction. So these are two systems, guys. This is an open system, and this is a what? This is a closed, sorry, this is a closed system because no non-conservative forces. And this one is an what? Is an open system because there is a non-conservative force, which is the what? The friction, right? Drawing the label free body diagram in 5.2, I'm gonna make an incline. Guys, you must remember to make an incline by the broken line if you're not gonna forget to make your so guys, at this point it's stationary, the velocity is zero, so there's a normal force that is perpendicular to the surface. We have a gravitational force, right, which is the Fg, and then since this object is standing here, chances that it can go down, so there's a frictional force that is going upwards. The frictional force, it's going to, guys, this object, they told us it's at a standstill there. So if it's at a standstill, the chances it can go down there, it's pulled by the gravitational force, but there will be a frictional force upwards. Guys, very important to understand that. I hope it makes sense. So we're gonna have a frictional force there, which is going to be Fs, right? So, and the Fg there. I hope I do make sense with that. Explain the term non-conservative. Again, guys, it's an exam guideline. Exam guideline definition, not the textbook. It's an exam guideline. A non-conservative force is a force for which the work done is dependent on the path taken. It's a force in which the work done is dependent on the path taken, right? Exam guideline once again. 5.4, calculate the angle theta of the slope if the skater experiences a frictional force of 20 while skating up. So we want this angle. So the frictional force while it skates up, it's what? It's 20 newtons. So very important. What we're going to use there, I'm going to use in 5.4, the work done by non-conservative. I'm going to use the work done by non-conservative. Work done by non-conservative, it's change in EK plus change in EP. It's going to give the same answer when using this work energy theorem. Both of these are work energy theorem, right? So it gives the same answer. The While it moves up, the non-conservative force that is acting here, it's the friction only. So I'm gonna do the work done by friction. Work done by friction is Fk change in x cos theta, and here it's half mv final minus mv initial. Guys, this is supposed to be p, and mgh final minus mgh initial. Guys, it's very important to write the formula properly. The frictional force, we are told it's 20, so it's going to be 20, and the displacement we do not have. You see, so we're going to have two unknowns here. We're going to have two unknowns. We are looking for the friction, sorry, we are looking for the angle, and we don't have the change in x. We do not have the change in x there. So I'm going to just put it like that. The change in x, we're going to first find change in x and then cos 180. All the time the friction is cos 180. And then the mass of it's 53. It's half 53, and the initial velocity, the final velocity, it comes to still, guys, we must remember here, the final velocity is 0, and the initial velocity, it was moving at 6 here. That means the velocity here is 6, so the initial velocity is 6, right? We're gonna use 6 there. I hope I do make sense when it comes to that. So the final velocity is 0, and the initial velocity is going to be 6 plus, and it's going to be 53 times 9.8. And then the height final, this is the height initial, which is 0. The height final is going to be what? 1.5. This height, so it's going to be 1.5 minus the height initial is 0. Guys, when you do the math here, you punch the entire thing there, you're going to get negative 174.9, and then this is going to be negative 20 change in x, and then you divide by 20, negative 20, so you're going to get 8,745 meters. That's the displacement. You get the displacement first because you both don't have the displacement and the angle. And then the next thing that we're going to do, we're going to do a trig ratio. If you see that we have a height that's 1.5 there, we're looking for the angle. Now we got the displacement. Our displacement there, it's 8,745 meters. That means it's our change in x. So what are we going to do now? We're going to say sine theta is equal to opposite over hypotenuse, which is the opposite. It's 1.5. That's the height. Divide by the hypotenuse, which is the hypotenuse is change in x, which is it's 8,745. And then we're gonna do the what we call that, it's a second function, or it's the arcsine. It's 1.5. In your calculator you press shift, and then your angle there, it's going to be 9,88 degrees. Get question 6. Let's look at question 6, which is the Doppler effect. It says an observer with a detector standing on the side of the straight road records the frequency of the police car siren moving in a straight line on two separate occasions. The police car moves at the same constant speed in both occasions, right? The results are shown. Guys, we are told that the observer with a detector is standing. That means the velocity of the listener is equal to 0. So it's the source that is moving, which is the police car, right? It moves at constant velocity. So this, it was recorded in two separate equation clearly while it was moving away and towards. So guys, let's look at the graph. Graph A, this is the frequency of the source, and if you look at the frequency of the listener, it's 1000. So once here, the frequency of the source is lesser than the frequency of the listener, so that means here it was moving towards, once the frequency of the listener is higher than the frequency of the source. Here we can see the frequency of the listener. The frequency of the listener is lesser than the frequency of the source. That means it was going away here. So those are the two separate equations. So this one, it's a frequency of the what? Frequency of the source. This one is the frequency of the source, and this one is the frequency of the listener. Now it says state Doppler effect in words. Very important, guys, to understand the definition of the Doppler effect. I'm just gonna say it. I'm not gonna write it, guys. You must memorize the definition. It's worth marks. It says the change in frequency of the sound detected by the listener because of the sound source and the listener have different velocities relative to the medium of the propagation. That's the definition, guys. I hope you paused the question. You have done the question by yourself before watching this. 6.2. 6.2. Okay, let's write it there. It's a short question. Which graph A, B shows the police car while it moves away with an observer? I already answered that. It's what? It's graph B. And let's say give reason for your answer. We're going to say the frequency of the listener is lesser than the frequency of the source. Now in 6.3, it says calculate the speed of the police car, right? And we are given the speed of the sound in the air is that one. Guys, very important to note what we have. So here in this case, we have the velocity of the listener is 0. They wanted the speed of the source, and both we do not have the frequency of the source. So now you have two unknowns. You don't have the speed of the sound, and you don't have the frequency. We were just told it's that line and that line, the frequency of the source. So this will be simultaneous equation. So I'll write the simultaneous equation. I'll start with the array. I'll create the equation. So if you have two unknowns, guys, simultaneous equation. I'll start with the array. The array, the frequency of the listener is 900. So the array, let's write the equation. It's going to be V plus minus VL over V plus minus VS times the frequency of the source. Now I'm substituting. The frequency of the listener is 900, right? While it was moving away is 900. So it's going to be 900, and the speed of the sound in the air is 340, and the velocity of the listener here is going to be minus is 0, and because it's constant, and 340 plus, and this is what they want to the VS, right? We wanted the VS, and the frequency of the source we do not have, so we are creating that equation there. So it's gonna be this is gonna be 0, so it's gonna be 340 fs over 340 plus vs, 900 there, right? And then we cross multiply, and when we cross multiply, it's gonna be 340 fs equal to 900 times the 340 plus Vs. We'll say this is our equation 1. Let's do equation 2 here. And let's do towards. Towards. So we're just going to substitute now. The towards we know, the away we know it's a negative, divide by the positive. Here it's going to be a positive divide by the negative. So we know the frequency of the listener, it's 1100. So it's going to be 1100 equal to the 340 plus 0, and then the 340 minus Vs, and then the frequency of the source we do not have again there. And then this is going to times that, so it's going to be 340 fs divide by 340 minus vs is equal to 1100. And then we cross multiply, we're going to have 340 fs is equal to 1100 into 340 minus vs. This is your equation 2, right? Now we're going to sub the equation 1 and equation 2. The commonality between the two is 340. We're going to sub the 340 and 340 there. So let's say we're going to say 340 fs is equal to 340 fs. So what we're going to do, we're going to equate to this side. We're going to say 900 into 340 fs plus vs is equal to this side. So it's going to be 1100, just a 20, 340 minus vs. And then what we do, we distribute that. The 900 times the 340 is going to be it's 306, right? Is it 306,000? Yeah. And this plus is going to be 900 vs, and this times this is going to be 37400. It's 374,000, and this times this, it's going to be minus 1100 vs. And then guys, it's the maths, and then our vs. So do you see the unknown now? It's vs. The fs, it has been eliminated, so your vs is going to be 34 meters per second. I hope I do make sense when it comes to that one. 34 seconds, 34 meters per second. Now 6.3, it says cow. We already done that. We already done that. It was a matter of copy and paste. 6.4. It says study emission spectra A, B, C of a distant star observed on Earth. So there's a star that is observed from Earth into a space. In the space, it says spectrum A is in the laboratory reference spectrum. So this one we're going to use as the reference. So these are the ones that are observed. We're going to use this as a reference. You see this side it's a red and this side it's a blue, right? So 6.4.1, it says which spectrum B or C that indicates the star moving away. Which one that indicates a star that is moving away is the one that is a red shifted. Is the one that is red shifted that moves, indicates the moving away. Guys, if you can draw the lines like this, do you see the lines are this is moving, this the lines are diagonally to the diagonally to the red shift. So this one, guys, is what is red shifted. This one is red shifted. Do you see the lines move towards red? So this one is what red shifted. And if you can make those lines with this one, do you see these lines are moving what are diagonally shifted towards what red, to blue, sorry, they are shifted towards blue. Do you see? They are shifted towards blue, those lines there. So this one is a blue shift. So the red shift, it shows that it was moving away, and the blue shift, it shows that it was moving towards. So the answer here is what? It's B. The answer was it's B, because it's what? Because it's red shifted. That's the reason. So you will say it's B because it's what? It's red shifted. B is red shifted. Now 6.4.2, if the blue part of the star spectrum is being observed from Earth, describe the frequency and the wavelength. So we should describe this one. The blue shifted, guys, all the time. The wavelength, you talk about the wavelength. What's happening to the wavelength? The wavelength is what is shorter. So the wavelength is what is shorter. It has a shorter wavelength. And then the frequency is what is high. The blue shifted frequency is high. But the red shifted, guys, it's an opposite of this, is a longer wavelength and a lower. Question 7 is the electrostatics. It says 2-point charges A and B are placed 3 meters apart. The charge A is positive 6 times 10 to the power negative 6, and the charge B, it's negative 3 times 10 to the power 6. P is 1 meter to the right of B. So here are the charges. This one, A, is positively charged and this one is negatively charged. The distance between them is 3 meters. And from B to P, which is this point, it's 1 meter apart, right? It says in 7.1, define the electric field at a point. This definition, guys, you can define by the formula that says electric field is equal to force over Q. The electric field is, when you define it according to an exam guideline, electric field at a point, it's an electrostatic force, which is the F, per, it's an electrostatic force experienced per unit positive charge placed at a point. So you can use that to define using the exam guideline. 7.2, it says calculate the net electric field. Before that, let's look at the field lines. Guys, this one is positively charged, so the field lines are going away like that. So the electric field that P experiences from A, it's gonna go to the right. It's gonna push it to the right. It's gonna push it to the right, and then the electric field, that the electric field lines of this one that is negatively charged, the field lines are going to are going to pull it to the left, right? This one, these lines are going to push it to the right, and then the B are going to are going to pull it to the left, right? Very important that. Now it says calculate the net electric field. Let's draw a free body diagram quickly of the electric field experienced by that one. So the free body diagram of A on P, as I've mentioned, is going to go to the right. A on P is going to go to the right. The A on P is going to go to the right. And then if you look at the distance, A on P is 4 meters. But at the distance of B on P, it's 1 meter. That means the electric field strength is going to be big. As I've mentioned, it's going to go to the left. So it's going to be bigger than that one because of the distance. So it's the electric field of what? Of B on P. Remember, why is it going to be bigger? But remember from the formula, the bigger the distance, the smaller the electric field, right? All right, as we see, the net electric field is going to go in this direction, right? Let's calculate in 7.2. So let's choose right as positive. Let's choose right as positive. So the net electric field is equal to the electric field of what? Of A on P plus the electric field of B on P. But let's look at the electric field of P on B on P. The B on P is going in this direction, so it's going to be negative, right? So it's going to be KQ. What is the charge? It's charge A divided by R squared plus, now it's not going to be plus, it's a negative times positive. It's going to be negative there. So it's going to be negative KQB over R squared, right? And then we substitute 9 times 10 to the power 9, and then the A, it's 6 times 10 to the power 6. 6 times 10 to the power 6, it's 6 times 10 to the power negative 6 all over the distance. It's 4. The distance, it's 4. So it's going to be 3 plus 1, that makes 4. That's where we get the 4. And then the Q, it's 9 times 10 to the power 9. 9 times 10 to the power 9, and the QB, the charge B, it's 3. It's negative 3, but we don't put the negative, and the distance is what? It's 1. The distance is 1. And then don't forget to square there. If you punch this in the calculator, you get the 23,625 newtons per coulomb. And the negative that you're going to get there, it means it's 23,625 newtons per coulomb to the left. Very important, that information. Right, 7.3, it says a proton is placed at P. Now, instead of just P there, or just an empty space, or just a point, there's a proton that is placed there. The proton, right? You know the proton, it's equal to the P is equal to, which is the elementary charge Q for the proton, is equal to 1.6 times 10 to the power negative 19 coulomb. So it's a proton that is placed there. It says calculate the magnitude of the initial acceleration of the proton if the mass proton is that one. We're given the mass of that proton and we know the charge of that proton there. So in 7.3, what are we going to do there? We're going to use the formula that says E is equal to F over Q. What do we want? Since we want okay, let me write the things that we have. We have the Enet, right? We have the Enet, which is this, and we are given the mass. The mass, it's 1.67. 1.67 times 10 to the power negative 27 kg. And then we have the charge. The charge, it's 1.6 times 10 to the power negative 19 coulombs. It's for the positive, which is for the proton. It's a constant. And then that means in order for us to get the acceleration, we must get the what? The F net, right? So this is the first thing that we're going to get through this formula to get the F net. So we use the E net to get the what? The F net. So the E net, it's 23,625. We want the F net. And then we use the charge, which is this 2. It's 1.6 times 10 to the power negative 19. And then when we cross multiply, we get the F net. When we cross multiply, we get the F net. Our F net, it's 3,78 times 10 to the power negative 15 newtons. And then the next step, we're going to get the acceleration now, the one that they want, using the formula F net is equal to ma. We'll substitute the 378 times 78 times 10 to the power negative 15 equal to the mass. We were given the mass, it's 1.67 times 10 to the power negative 27. And then we want the acceleration. We divide by that. We divide by 1.67 and we get the acceleration, that is 2.26 times 10 to the power 12 meters per second. Don't forget the units. This is the final answer that we needed there. Now 7.4, it says if the electron was placed at point P instead of the proton, right? Instead of the proton. Guys, what do we need to understand? The proton has a smaller mass than the electron, right? The proton has a smaller mass than the electron. So now it says, what would the acceleration of the electron compare to the acceleration of the proton? Yeah, it's gonna be 7.4. It's gonna be larger than. Why is it going to be? It's gonna be a larger acceleration. Why is it going to be in a larger acceleration? Because the mass of the mass of the electron is smaller than the proton. So the smaller the mass, the larger the acceleration. From this, that says acceleration is inversely proportional to the mass. The smaller the mass, the larger the acceleration. But this is going to happen in what? In opposite direction. Opposite direction. So this acceleration are going to be in opposite direction. Remember, the electron is negative and the proton is positive. So they're going to go in opposite direction, right? Very important for that. Now let's go to the electric circuit question, which is question 8. It says a battery with an unknown EMF. So we're not given the EMF there. Very important information. Now it says an internal resistance with 1 ohm connected with 3 resistors and a light bulb and a high resistance voltmeter, a switch and an ammeter of negligible resistance is shown below. Now it says the resistance of the bulb is 4 ohm, and the resistance of the 3 resistors, it's 3R, it's 2R, 1R and 6R respectively. So guys, let's look at the circuit. After reading the statement, you follow the current there. So we have a total current there, total. When it gets there, this is the total. When it gets there, it splits. There's a split that goes there, right? And there's another split. There's another split that goes that way, right? There's another split that goes that way, right? It's very important that. And then it combines again. And then it combines again. It's a total current. That means it's a total current that passes here, right? So what we have, it's a total current. The current there, it's a split, right? So what we're noticing here, we have 2 resistors in series in this parallel section. So it's 2R and 1R. So this makes what? 3R. And then this is 6R. Oh, that simply means that the resistance of this part is the half of this one, right? So if the current here, the current that passes here is a 0.2, that means the current here, it's a double of this. I'm going to prove it by calculation. The current that passes here, it's a double of this one, because the resistance of this, that's a half of this one. Remember, the resistance and the current are inversely proportional, right? Sorry, right? Very important, that information. And while the switch is closed, and this is a series circuit, the total current passes there. Now, 8.1, it says define the term EMF. Again, guys, exam guideline. The EMF is a maximum energy provided by the battery per coulomb charge passing through it. Maximum energy or total energy provided by the battery per unit charge passing through it, which is through the battery. Use the exam guideline. 8.2, it says when switch S is closed, the current through the ammeter at 0.2 and the potential difference across R1 is 6 ohms, right? Is 6 ohms. So now it says here, write down the value of V2. Write down the value of V2. Where's the V2? The value of V2 is this one, right? We're told that the R1, the voltage here, it's 6V, right? It's 6V, the voltage there. And then if you can see, if the resistance here is 2 times than the resistance of this one, right? That means the voltage of this one is the half of this one, right? So if the voltage here is 6V, that means the voltage here is 3V. Remember, there's a direct proportionality between the resistance and the voltage, right? So it's 6V, it's going to be 3V, right? Very important. Now, if the voltage of this path of this is going to be what? It's going to be 9 volts. That means the voltage here, it's also 9 volts, because it's 6 plus 3, it's 9, right? Now the answer here, now to answer this question, it's gonna be 3 volts, right? It's gonna be 3 volts. And then it says the current through the R2. Where's the R2? The R2, which means the current that passes here. I told you that the current here it's 0.2, and that the resistance here, it's the half of this resistance here. That means that the current that is gonna pass here, it's a double of this one. So it's gonna be 0.4 amperes. I would like to prove it to you. Why? Now, let's say, let's use the calculation to prove this. But there's no need, it's 1 mark. I just hope you understand that. But we can say the current that passes here, that's what we want. Let's say it's 3R, because it's 2R plus 1R. Let's say the current, let's say in R2. And then we're gonna say, since we wanted the current that passes here, we're gonna use this one. We're gonna say 6R over the total. It's a 3. Remember, 2 plus 1 is 3, and 6 is gonna be what? 9. 9R times by the total current. We want to get the total current, right? We want to get the total current. So in order to get the total current there, we take this current here, this is 0.2, we substitute it here, and then it's a 6 over 9, and we times by total current. We want the total current. The total current is 0.6. The current that passes here, we want the total current that comes there. So we're gonna say 0.2 divided by this, 0.2 divided by 6 divided by 9, it's 0.3. Something not correct. It's 0.3. What we do, it's 0.2 divided by 6. Okay, we want the current that passes where? We want the total current. So we say 0.2 we divide by, it should give us divide by 6/9. It gives us 0.3, right? Okay guys, let's leave the proving of that, because I do not find it. What am I missing here? We have the current here. Oh, I'm supposed to do the other way around. I'm supposed to do the other way around here. I'm supposed to say I'm supposed to say 3r over 9r. So it's going to be 3 divided by 9. So we divide by 3 over 9. So it gave us 0.6. That's correct. So the current here, the total current here, it's 0.6. 0.6. Why? That means the current that came here, it's 0.6. And then there's a split. If from 0.6, this one, it's 0.2 that goes this way. That means this one is 0.4. Remember, I told you that the current that passes here, it's 0.2. So the current that passes here, it's a double of this one, sorry. So it's 0.4 and a 0.2 that makes 0.6. So that's how I prove it. Guys, if you don't understand, you don't have to, right? You don't have to. 8.3, calculated resistance R3. So we want R3. Where's the R3? Is this one. So the R3, so what we can do in 8.3, we can say R is equal to V over I, right? Because we know the voltage there, we got it from, remember I said it's 3 volts plus 6 volts, it gives 9. The voltage here, it's 9, and the voltage there is going to be 9. So we're gonna say 6 plus 3 divided by the current. The current that passes here, it's 0.2. That's 0.2. So the current there, it's going to be 9 divided by 0.2. The resistance is going to be what? 45 what? Ohms, right? Let's go to 8.4. 8.4, it says calculate the value of the EMF. So the value of the EMF, how are we going to calculate that? If we can find the voltage first, the voltage in parallel there, it's 9. Remember, how did you get the 9 again? It's 6 plus 3, it's 9. That means it's 9, right? So the voltage in parallel there, it's what? It's 6 plus 3 again, it's 9 volts. And then the current there in parallel, which is it's a total current as well. So it's a 0.2 plus 0.4 is equal to 0.6 amperes. Remember, they ask us, it's 0.4, and I've tried to prove the 0.4. So that's what we have there. So we can get, now from getting that, we can get the RP. We can calculate the RP. R parallel is equal to V parallel divided by I parallel, which is the current that moves here in the parallel. The current that moves here in the parallel is the total, which is just 0.4 and the 0.2 in combination. So we can say here, we can say 9 divide by 0.6, which is going to be what? 15 amperes. Now we have the resistance in parallel, right? What are we going to do with the resistance in parallel? We can do the R external. The R external, remember, it's R parallel plus what? R series, which is the R parallel is what? Is 15, and the R series is what? It's 4. That makes what? 19 ohms. So we can go straight to the formula that says EMF is equal to I times R external plus R internal. So we're looking for the EMF. And the total current, remember, it's this one. I told you the current that moves in parallel, it's the same as the current that is total. And the R external is what is 19, and the R internal, it's 1. We were told in the statement it's 1. So it's going to be, the answer there is going to be 12. It's going to be 12 volts. That means our EMF is 12 volts, right? I hope I make sense there. Now in 8.5, it says in a separate circuit, the variable resistor is connected to the battery with an unknown potential difference as seen as the following. Here's the variable resistor. So now it says the graph below shows the relationship between the power dissipated in the resistor and the resistance of the resistor, right? So we have this graph. It's the power and an inverse of the resistance. From this formula, we know, guys, we know the formula that says power is equal to V squared over R. We have an inverse relationship between the resistance and the power. The greater the resistance, the smaller the power. But in this graph, they have made an inverse of the resistance. That's why they have a direct relationship. Now, in this question, they said use the graph to calculate the potential difference across the resistor, right? Now, to calculate the potential difference across this resistor, first, why do we have to calculate the potential difference across this resistor? The potential difference across this resistor, guys, it's there, it's the gradient, right? It's the gradient. Let's see if it's a gradient. Let's say the gradient is equal to change in y over change in x. What is my change in y? It's p. And my change in x, it's an inverse of the resistance. Inverse of the resistance, right? So here now, we are going to change this division into multiplication. So we're going to say p over 1, and then we change this division into multiplication. It's going to be r over 1. So it's going to be p times r, right? And then we substituted the p with this formula. So it's going to be v squared over r times r, which is going to be r over 1, and this r will cancel. So we're going to be left with v squared. So the gradient here is the v square, right? That's the gradient. So that's what they want here. That's what they want here. So they want the gradient, which is the v square. So what are we going to do? We're going to take 2 points. I'm going to take the point here and that point. This point here, it's 0 into 0. And this point here is it's 10 into 1000, right? So when we calculate the gradient here, which is the v square, the gradient, it's the v square, it's the change in y minus change in x. So it's going to be y2, which is the 1000, minus the y1, which is 0, and over x2, which is the 10, minus x1, right? Minus the x1. X1 is 0. So it's going to be 1000 divided by 10. It's 100, right? And then it's a v square. Remember the question, it wanted v. V square is a gradient, but we can get the v, right? So we'll put the square root of v is going to be 10 volts. That's the gradient v. I hope it makes. Let's look at question 9, the electric machines, the electrodynamics. Study the diagram of a simple generator below and answer the following question. We're told that this is a generator. And what type of generator is this one? It's an AC generator. 9.1, it says, is this an AC or DC generator? It's an AC. The reason for that, we'll say there is a or there are slip rings. There are slip rings, right? State the energy conversion. Always the energy conversion from the generator. It's mechanical to electrical, to electrical energy all the time, right? 9.3, it says in which direction will the induced current flow, state only A B to B C, A to B or B to A, right? Guys, since it's a generator, we'll use the right hand rule, and your forefinger, I don't know which finger, the pointing finger must point to the south, right? It must point to the south, and and we're gonna take this side, the AB. So the thumb is going to be up there, and the pointing finger is going to point to the south, and you will notice that the middle finger, the one for current, it's going from A to B. So the answer there, it's what? It's A to B. The answer is A to B, right? The diagram below shows the EMF time graph of one complete rotation. And as we can see, we're given the EMF there, the maximum, and the period there. Now it says calculated resistance. Calculate the resistance of the load. So we want the resistance of this load, right? The resistance of the load, if the IRMS is that one, when the Vmax is 150. So what we're going to do, guys, in 9.4, we are looking for the resistance, right? So we're going to change this IRMS into IMAX. So I'm going to change the IRMS into IMAX. So I'm going to use the formula that says IRMS is equal to IMAX divide by square root 2. And then the IRMS, it's 4,55, and then I'm looking for the IMAX. What is the reason for me to do that? I'm going to use the formula of the resistance that has the RMAX, the IMAX, and the Vmax. I'm going to show you. And then we cross multiply. The IMAX is going to be, when we cross multiply, is going to be 6, 4, 3, 4 amperes. That's the that's the what? That's the RM, the IMAX. So the formula that we're going to use is going to be the formula that says Vmax is equal to IMAX. That's the reason I started to change the IMS to that one. So the Vmax, it's 150. We have the Vmax, it's 150. 150 divided by 6.434. So the answer, it's gonna be 23,31 volts, not volts, ohms. That's the resistance of that load there. 9.5, it says the other load is now replaced with the bulb with the power consumption of 400 watts. So the power, it's 4. This is the power, and use the assume that the bulb is 100% effective, and calculate the light energy emitted by the bulb in 3 seconds. So what do we have? We have time, and the efficiency is that one is 100%, so it works entirely. So we're gonna change the 3 minutes into seconds. It's gonna be 180 seconds. It's gonna be 3 times 60, it's 180. So I'm gonna write the answer here. It's 9.5. 9.5. So what are we looking for? We're looking for the energy. So we have the formula that says power. We're going to use the formula that says W is equal to, no, we're going to use the formula that says power is equal to W over change in T. So this is what we're looking for. We have time, we have power. So we substitute the power, it's 400, and the energy is the one that we're looking for, and the time is 180, and the energy is going to be 72,000 joules. That's the energy emitted by the light bulb. Now it says the speed of the rotation is now doubled. Guys, all the time when the speed is doubled, the EMF is what? Is doubled, right? The speed, when is doubled, when the speed is doubled, that means the EMF was going to be also doubled, right? Now it says redraw The above graph in the answer book on the same set of axes and indicate the old and the new pattern. Label the new as B, right? So guys, I'm not gonna draw another one. I'm gonna use this one. So what I'm going to do here, if the speed is doubled and the voltage is also doubled, let's say this is 300 here. Let's say this is 300, right? And also the time, the period, guys, is going to be half. The period is going to be halved. The period is going to be halved. It's going to be halved t, which is the period. This is the time when it was 150. So the graph is going to be like this, guys. It's going to be like this. Don't know what I'm doing. The graph is going to be like this, and then it ends there, right? The period now, it's 0.1, it's halved. And do you see the EMF is double? That's 300, right? That's the graph, and they told us the graph, the new graph, it must be B, so we label that one B. Okay, let me also label it there. It's B. As you're going to be given a graph paper with the original, a graph paper with the original. So you're just going to draw this one there, right? And 9.6.2, it says with what factor will the energy emitted change if the speed of the rotation is doubled? Which is just 2 times faster. It's 4 times. Guys, from the formula that says power is equal to W over change in T. We know the power from the formula that says power is equal to V square over R square. As we mentioned, guys, that, okay, let me substitute this so that you can see something. The power is equal to V square over R equal to W over change in T, right? W change in T. So when we cross multiply here, we're gonna have W is equal to W. It's gonna be WR. Come on, it's gonna be WR when you cross multiply, and V squared times change in T and over R. So when we remove the R there, when we're gonna divide by R there, we remove the R, so we have W is equal to that V squared times R over not R, change in T over R. So now, guys, if you look at the W and the R from this formula, and the V squared from this formula, and the V squared, so if the V squared is doubled, so it's going to be double V square, right? It's going to be 4V square, so it's 4 times. Do you see? So that means this one is going to be 4 times as well, right? So that's why I'm saying the factor here, it's going to be 4 times the energy. 4 times the energy. It says explain your answer. So when explaining the answer, it's going to be 4 times, or you can say 4W. So when explaining that, you must state that the EMF that is induced is inversely proportional to the what? To the time. The shorter the time, the greater the EMF. So the faster the coil, when you double the speed, that means you are shortening the time, the EMF will increase. That's very important, right? So this is when if the flux is what? Is constant. They are inversely proportional, these two, if the flux is constant. This comes from the formula from grade 11 that says change in flux times by the number of 10 change in T. So if the flux is constant, these two are inversely proportional, right? Okay, let's leave that. And another point here that you need to state, if the rotation is doubled, the induced EMF is doubled, right? That's what we have seen. If the speed or rotation is doubled, then the induced EMF will be also doubled. That's what we have seen there. And the last point there, remember this is 4 marks. You must state 4 points. The last point there, you must state, as I've mentioned there, that point there, that the energy is directly proportional to the squared voltage, or the squared voltage, only if the R from this formula, the T and the R, they must be constant. If the change in T and the R is constant, they must be constant to have that direct relationship there. I hope, guys, I do make sense. Let's go to the next question. The next question is it's the last question. It's the photoelectric effect. The photoelectric effect, it says, in an experiment, different light sources are shown into the surface of an unknown metal. So yes, the UV light is shown into this metal, and then the photoelectric effect occurred there. Now, 10.1, it says, explain the term work function. Guys, when we explain the definition, again, it's an exam guideline. The work function is the minimum energy that the electron in the metal needs to be emitted from the metal surface. Minimum energy that is needed, the electrons need to be emitted or ejected from the metal surface, right? 10.2, it says, the electrons with the maximum kinetic energy. Here's the kinetic energy. We have a kinetic energy there, are emitted from the surface of the metal when an ultraviolet light with a frequency of this is the frequency of ultraviolet, this is the frequency of the light. Now it says the question, calculate the work function of the metal. So 10.2, I'm going to do it today. We're looking for the work function. We have the EK max, which is this, and we have the frequency, right? So we are looking for that. So what we're going to do, we're going to use that formula that says E is equal to a work function plus the EK max, right? So, and then we substitute the, right? We're gonna use the HF for energy because we're given the energy of the light, and we are looking for the work function and the kinetic energy we are given. So we substitute. So it's gonna be 6.63, which is the H, the Planck's constant, times by the frequency, which is 1.2 times 10 to the power negative 19, equal to the work function that we want plus the kinetic energy. No, this is incorrect. So we times by, let me use the bracket, we times by the frequency, which is going to be 6.63 times 10 to the power 14, which is, this is the frequency, 14, and equal to the work function, the one that we want, and the kinetic energy, it's 1.2 times 10 to the power negative 19. And then we do the math. We take this to this side after multiplying, and then we're going to have the work function, that is 2.98 times 10 to the power negative 19 joules, right? That's the work function there. We are done with that question. It's simple as that. Now it says, will electromagnetic radiation with a frequency of this is the frequency of the other light, emits the electron from the surface of this metal. Choose. So now what do we need to do first? The answer is yes or no, but you have to calculate first before you can conclude if the answer is yes or no. So it says support you with your answer with a suitable calculation. Now what we're going to do, we are going to First, it's 10.3. I'm gonna use the work function of this metal and get the threshold frequency and then compare with that. So we're gonna say work function is equal to Planck's constant times the threshold frequency, which is a 6.63 times 10 to the power negative 34. We are looking for the threshold frequency so that we can compare with this one of this metal. And the work function we do have the work function there. So it's 2,98 times 10 to the power negative 19. And then we divide our threshold frequency there. It's gonna be 4,49 times 10 to the power 14 hertz there. And then now that's when we can conclude and compare. So we have this frequency and this. So this metal, so the answer here, the threshold frequency of this metal it's smaller. So do you see this is 14 and this is, don't look at only the values, you must look at the powers. So the answer is yes. Yes. Why? Because we're going to say the frequency, the frequency, the threshold frequency of the metal is lesser than the frequency of the light, right? That's what we're going to say there, and then you get your full 3 marks. Now let's look at 10.4. 10.4, it says when a photoelectric effect is demonstrated, a negatively charged plate is used. So in order for a photoelectric effect to take place, this plate must be negatively charged. But we can see here it's positively charged. It's explain why when an ultraviolet light is shone into a positive charge plate, no charge is lost by the plate, which is no photoelectric effect has occurred. So it's easy to explain this one. So the first answer you can say the photoelectric effect, it has to be positive. It's a straightforward. The photoelectric, if the plate, it has to be positive. So what we can do, you will say no free. When something is no free electrons, no free electrons to be removed. There will be no free electrons will be removed there. When something is positively charged, guys, that means the protons are more than the electrons, right? And then the next thing that we'll do, the plate, you can say the plate is positively charged. The plate is positively charged, and which is lacks electrons. It has an electron deficiency, right? Then another thing that you can say there, you can say electrons can be only removed can be only removed on a neutral or a negatively charged plate, right? That's how you answer that one. The plate is positively charged and few electrons are available. You say there's a lack of electrons. And another thing that is important there when answering, no change in the charge plate will be observed, no photoelectric effect. Therefore, no photoelectric effect will take place there. Right, that's the end of the question grade 12. I hope you enjoyed this question paper and it helps you to gain the skill of answering some of the question. Thank you very much. All the best.